Hello, welcome to today's edition of Yebo Tutors. We will be looking at physical science, paper 1, and with most of you requesting that we look at projectiles and also some part of work and energy, we'll try and look into that today. So I hope you guys are benefiting from these videos. For those that are not able to join us live, you are welcome to still give us your comments after you see the recordings from our channel. So we have a paper. This is a paper from November 2016. And we're going to start with question number 3. So I'm gonna connect the tablet so that we can start. Let's see if it's connected. Okay, good. So now we can start. Got on a fresh page like that. Well, so question number 3 will be our first one, and with this one we have, let me just give you a zoom in into that question. There we are. So a ball is dropped from the top of a building 20 meters high. Ignore the effects of air resistance. So there is the diagram with a ball from the top of a building. The building is 20 meters high. The first question says define the term free fall. So this is a freely falling body. What does it mean to say the body is in free fall? So for a body in free fall, what it simply means is the gravitational force is the only force that acts upon that body. There is only the gravitational force acting upon that body and no other additional force. So that's the meaning of what the term free fall would imply. So this is motion under the action of gravity only, or gravity alone. Then part 3.2 says calculate A, or 3.2.1, the speed at which the ball hits the ground. So take note, with such kind of questions, you are usually not given the initial velocity. It is something that you should deduce from the statements that are given. So in this case, you are told the ball is dropped and not thrown. It is only dropped through that height. So which means initially it has 0 velocity. Its initial velocity is 0, and it gains velocity under the action of gravity until it touches the ground. So what we can do, the best thing is to always put together the data that is available from what you have in the question. So like we have in this case, we've said our initial, let's call it V initial, is equal to 0 meters per second. Initially, the ball is stationary, and on release, when it is dropped, it starts from 0 and increases its velocity. Then we are not given the final, so that's not available. But we know that it moves a distance s, which is 20 meters. And what it means is this displacement, 20 meters, we have already chosen the downward direction as, yes, positive. As positive. The downward direction is positive. So this distance will be positive 20. And which means already you'd expect a positive velocity there. Sorry. I didn't show that. Okay. So I said we've got an initial velocity Vi, which is 0. We have the final velocity, which we are not told, we don't know. Maybe we might need to calculate it at some point. But we have a displacement downwards from the dropping position at the top of the building and 20 meters to the ground. And we have said the downward direction is positive, hence we have a positive displacement. Then we have an acceleration, which is positive g. G being 9.8, right? So since we have taken the positive direction to be the downward one, then g is positive 9.8. Okay, so to answer the question, the next thing is the equation. You need to identify the best equation to use to answer this question. So at the back of your paper, you can recall that you have a list or a catalog of equations. If you don't remember them clearly, or you don't recall them by head, then you can refer to those, but you should be able to use the most appropriate. So now the speed of the ball when it hits the ground is basically Vf. We want to find Vf. So for us to find Vf, we need an equation that relates Vf to the quantities that we have already. So we have S, we have Vi, we have A, we don't have T. So which means you won't use any equation that has T. Therefore, to find the speed with which the ball hits the ground, that speed is Vf, is equal to, so we can use Vf squared equals to Vi squared plus 2As, where Vf is what we need to find. Vi is 0, A is G, which is 9.8, S is 20, they're all in the same direction. And that means what we are looking for there is V final being the square root of 2 times 20 times 9.8. So we want the square root of that. The square root of 2 by 20 by 9.8. And what you get there is 19.8 meters per second. Good. So this is the speed at which the ball hits the ground, 19.8 meters per second. Don't leave your units. Don't leave your units. All right. So that's the first part. Then the next part, 3.2.2. The time it takes the ball to reach the ground. So now we want time. So you recall also this equation, Vf equals to Vi plus At, right? So we have VF now, we have VI, we have A. We can find T. So T equals to VF minus VI, final velocity minus initial velocity over the acceleration due to gravity. And therefore, we use our VF 19.8 minus 0 over 9.8. And that gives us T equals to, you can calculate, you can also calculate that, see what you get. Divided by 9.8, 2.02 seconds. Okay, so far so good. So this is basically how simple it is to deal with projectiles. So this is a part on vertical projectiles. When we extend to two-dimensional motion or projectiles that are projected at an angle, then as they describe that parabolic path, we still include the same principles in our calculation. So it is important that you look at the vertical motion of that projectile individually, then also look at the horizontal motion separately. Then you can combine the two to come up with your final answer. It should always be a straightforward thing. Okay, so let's just proceed to the next part. I'm sure 3.3. Part 3.3 says, make a sketch of the velocity time graph for the motion of the ball. No values are required. So this is just a sketch. In your sketch, you already picture in your mind of some object that is starting with a velocity of 0. So you start at 0 and t is 0. Then the velocity of this object is increasing to a certain quantity, which we don't want to know what value it is, at what time it is. That's not a problem. But what is important is what makes that velocity increase. It's acceleration, and this acceleration is uniform. So it means it increases the velocity equal quantities at equal intervals of time. So it's a uniform velocity, hence it's a uniform acceleration, hence the velocity also increases uniformly with time. So that means we should have a graph with a constant gradient, Let me use a different color. Sorry. Like the blue. So it's called a velocity versus time graph. So you have your time in seconds on that axis and velocity in meters per second on the vertical axis. The velocity starts from 0, so it should start from this origin and increases gradually or uniformly like that. So at equal intervals of time, the velocity also increases by equal amounts. This is what we mean. Let me just, this is no longer part of the sketch. The sketch should just be something like this. So if we have those as time intervals, that then we are saying the velocity increases by that amount in the first interval. Then this is the same amount. This is the same amount by which the velocity increases in equal time intervals. So already it means from your knowledge of graphs, if we take the gradient there, this gradient will be Let's say we have VF there and VI there. Or let's put VI back at 0. This is VI. Then we have the gradient will be VF minus VI over T minus 0. And you can already see what this equation is. VF minus VI over T. This is similar to the acceleration. VF, where do we have VF minus VI? Okay, so which means it's a rearrangement of this part. It's a rearrangement of that. If we make G the subject, then VF minus VI over T will be the acceleration. So the gradient of that velocity time graph gives you an acceleration. Okay, so that's the sketch. The sketch should be your vertical axis, horizontal axis, and the line. That should be straightforward and clear for you. Let's see what follows after that. That's question 4 on momentum. So we'd also want to look at a question paper with motion in 2 dimensions. So we'll look for one. If you know of one, you can also update us on it and tell us where we can find that question and we can tackle it together. Okay, so let's look at question number 4, which is showing right now. The graph below shows how the momentum of a car A, changes with time just before and just after a head-on collision with car B. Car A has a mass of 1,500 kgs, while the mass of car B is 900 kgs. Car B was traveling at a constant velocity of 15 meters per second west before the collision. Take east as positive and consider the system as isolated. Consider the system as isolated. Now the question goes, then there is the diagram. We have momentum on the vertical axis, time on the horizontal axis, and the change in momentum is shown at some point in time when the collision happens. What do you understand by the term isolated system as used in physics? Isolated system. So these definitions are important. These are just extra marks for you. So make sure you are at the top of your game when it comes to these definitions and scoop all these 3 marks that are designed for you to benefit as much as you can. So isolated system. What do you think is an isolated system? Okay, so for an isolated system, this is a system which excludes external forces. So it is not under the influence of any external forces. Or if the external forces will be there, then the net external force will be 0. The net external forces on that system would be 0. Net external force. So it is one in which the net external force is 0. Meaning if there are external forces, they all sum up to give a net external force of 0. Otherwise, it is a system with no external force. It excludes all external forces. Okay, so the next part, 4.2, says calculate then the magnitude of the velocity of car A just before collision. So we're given also the quantities. Let's look at the quantities first. What quantities do we have from the graph and the information? Car A, mass A is 1,500, and that's in kgs. Car B, which is mass B, is 900 in kgs. The velocity of car B, VB, is 15 meters per second west. Take east to be positive, so the velocity is minus 15 meters per second. So this is the deduction that you should be able to quickly do and go on. Then we are also given the momentum from the question, initial momentum of A. This, take note, this has been drawn for car A. This is the graph for the momentum of car A before and after it collides with B. So this is for car A. It has got M, V, A, an initial of 30,000 Newton second, and, or you can say kgs meters per second, mass times velocity. And it has got a final of 14 kilonewtons second. All right, so I think we've just taken all the information that we may need, and the time there, delta t, is 20.2 minus 20.1. Okay, so delta t equals to 20.2 minus 20.1, which is 0.1 seconds. With that, magnitude of velocity of car A just before collision. So just before collision, car A has that momentum and car A has that mass. So which means we have initial momentum equals to the mass times initial velocity. So initial momentum equals to mass A times initial velocity of A, the magnitude of the velocity just before collision. So in other words, we can say, we can look at, where is the graph? Here, where there is no change in momentum, and say the change in momentum for A will be equal to, it has got a momentum of, an initial momentum of 30, so equals to final momentum minus initial momentum. So the final momentum will be at this point, which is the point just before collision. So final momentum minus initial momentum, the initial momentum being 30, but the change there is 0. And the final momentum is mass A times V final just before collision minus 30,000. So we could use this where we say the momentum there is just 30,000, it's just the same thing, equals to 1,500 times VA initial. So this is what this still gives us, 30,000 equals to MA times that velocity before collision. So which means this velocity before collision, we've already labeled it as final for the case where it is the final velocity just before the collision. It will be 30,000 all over the mass. So that's 15, 20 meters per second. For some of these calculations, you don't need a calculator, right? So we have 20 meters per second just before collision. Oh, I forgot about this big window. Sorry about that. I hope I'll get used to it soon so that we don't continue having to repeat. So we have here we took all the quantities that are given in the question, the mass 1,500 for A, 900 for B, the velocity minus 15 meters per second, then the momentum initially 30,000 and after collision 14,000, and the time when momentum changes 0.1 seconds. So we said if the change in momentum during this part, during this section, the horizontal section, the initial horizontal section of the graph up to the point of collision, then it means the change in momentum there is 0, and it should be equal to the final momentum before, which is the momentum before, right, just before collision, and the initial momentum, which is the 30,000 that we can see. So that will give us a velocity, an equation where 30,000 equals to mass times velocity, and the mass for A, we know the velocity will be 20 meters per second. So in other words, in simple terms, we're saying the initial momentum, which is 30,000, is equal to mass times the initial velocity. And we can simply divide that and we get VA, initial velocity for A, is 20.0 meters per second. Okay. So that's the first part for 4.2.1. 4.2.2 says velocity of car B just after the collision. So after the collision, what do we know about car B? We know that there is, for an isolated system, momentum is conserved. There is no net external force, or the net external forces will be 0 for this system like we defined. So momentum will be conserved such that the mass of A initially times the velocity of A initially plus the mass of B initially times the velocity of B initially should be equal to the mass of A. Okay, so the masses, they don't change, so I'll remove that. The mass of A times the velocity of A final plus the mass of B times the velocity of B final. So take note, the directions are important here. So you plug in the values of these quantities with their respective directions. So the mass of A and the velocity of A initially, which is the initial momentum, is 30,000 plus 900 times negative 15 meters per second. Confirm. Yes, negative 15 meters per second. So momentum is a vector. So when we add the vectors, we add them vectorially with respect to their directions. And the mass there, 1,500. Okay, we know actually this mass times velocity for A finally, and we can pick that from the graph, and that's 14,000. So we have 14,000, the final momentum of A, plus 900 times the final velocity of B. So what does that mean? Do the mathematics. You can try it from your calculator on your own. 30,000 minus 900 by 15. This is 16,500 minus 14,000 equals to 900 times V, velocity of B final. And what is 16,000 minus 4,500? That's 2,500 over 900 equals to VB final. 25 divided by 9 is 2.78. 2.78 meters per second equals to the final velocity of B after collision. That's the final velocity of B after collision. Then the next part says the magnitude of the net average force acting on car A during the collision. The net average force that acts on car A during the collision. So what do you recall? For you to relate force to this, you have Newton's second law, right? Newton second law relates force to the rate of change of momentum. In other words, so from Newton's second law, the net force is equal to the product of mass times acceleration, and this is mass times V final minus V initial over T, which is mVf minus mV initial over the time it takes for the change. That's equivalent to the force. So the force that is present in this system during the collision is the net average force that changes the momentum of the colliding bodies. So that means we can use the same principle to say F equals to mass of A. So this is acting on car A. That's why we're dealing with A. Mass of car A times velocity final of car A minus mass of car A times velocity initial of car A over the time delta T. And this initial, the final momentum, 14,000 minus 30,000 over the time it takes. What is the time that it takes? We said delta T is 0.1 seconds. So 16,000 over 0.1 That's 160,000 negative newtons. So the question says, take note magnitude. The magnitude. So this negative implies the direction of the force is opposite to the initial direction of motion of car A. So that's why it is a negative. So for magnitude, that force, that average force is simply 160,000 newtons. So take note, these terms that the questions use are very important to note. Magnitude means you just want the size of that force without mentioning the direction, without special mention to the direction. So the magnitude is 160 kilonewtons. Okay, yes, there's one on energy. Wonderful. So question number 5 looks at energy. We can look at question number 5. Together. So let me screen the big one and prepare some space there. Question 5, start on a new page. A pendulum with a bob of mass 5 kg is held stationary at a height h meters above the ground. Right? When released, it collides with a block of mass 2 kg, which is stationary at point A. So here is the diagram, height h, where the bob is displaced, and when released, it swings and collides with a 2 kg block at position A, which is vertically, which is just vertically below the point of suspension of the pendulum. Okay, so the bob swings past A and comes to rest momentarily after at a position 1/4 h above the ground. The diagrams below are not drawn to scale. So immediately after the collision, the 2 kg block begins to move from A to B at a constant speed of 4.95 meters per second. Ignore frictional effects and assume that no loss of mechanical energy occurs during the collision. So this is another isolated system. Calculate the kinetic energy of the block immediately after the collision. Okay, that's an interesting one. Question number 5. So we're 5.1.1. What can we say about the kinetic energy of the block from the given information? So I'm not gonna list the information now. I think we have lots of it. The mass of the block is, of the bob is 5 kg, but it's important though. Mass of bob. So we have a bob and we have a block. So we'll use big B for the bob and small b for the block, or the other way, small b for the bob. I choose small b for the bob. Mass of bob, 5 kgs, though the bob is actually heavier than the block. Mass of block, 2 kgs. That's everything else is in the diagram there. Okay. So take note the rest position, which means initial h initial is a height h, and h final is a height 1/4 h. So that's why it's important, so that you don't miss any of the information that would make it easier for you to solve the problem. So for 5.1.1, the kinetic energy of the block immediately after collision is given by this statement. It is in this statement there. That part gives us the answer. Immediately after the collision, the block moves from A to B at a constant speed of 4.95 meters per second. So this is the kinetic energy of the block. This is the velocity, which is responsible for the kinetic energy. So kinetic energy, we can use a letter EK. Kinetic energy is equal to half mv squared, which is half the mass is the mass of the block 2, and the velocity were given 4.95. So the kinetic energy is simply equal to squared to 4.95 squared, 24.5. So this is the kinetic energy of the block immediately after the collision. Then calculate also the height h. So for the height h, (5.1.2) height h. How do we do that? So we would, since this is a isolated system, we know that the change in the potential energy is equal to the gain in the kinetic energy. And this change in the potential energy is mass of the bob times g times h okay, it will be final potential minus initial potential equals to the final kinetic energy minus initial kinetic energy. And the final potential energy there is m for the bob times g times h over 4, which is h final according to that, minus m for the bob times g times initial h equals to final kinetic energy. We said we got 24.5, and initial is 0. Initially the block is stationary. So we only have one unknown, which is h. How do we put, we can factor out h, and we have mb times g multiplying 1/4 minus 1. So we have h multiplying mb, the mass of the bob is 5 kgs, times 9.8, which is g, multiplying 1/4 minus 1, negative 3/4. Equals to 24.5. Okay, so what we get there, we have 24.5 divided by 5 times 0.75 times 9.8 with a negative, which is 0. H equals to negative 0.67 meters. 0.67 meters. So because the change in the momentum, in the potential energy is a decrease, and the change in the kinetic energy is an increase, then which means H is actually below the initial height, and if measured from the ground, then that would be positive 0.67. So that will be H equals to 0.67 meters above the ground. So this is minus 0.67 meters below its initial position, and that's 0.67 meters above the ground. Okay. So that's below its, I forgot about this again. We started from here, so that means I'm gonna repeat. Sorry guys. Okay, so we say the mass, I'll just do that. I'll go through that one faster. The mass of the bob 5 kg, the mass of the block 2 kg, the initial height is H, and the final height is H over 4. Then we said the kinetic energy, we had found that kinetic energy, we found the kinetic energy by just multiplying half times m times the velocity that we highlighted here, 4.95 squared, and that gave us 24.5 joules for the kinetic energy, which was the answer to part 5.1.1. And when we went to 5.1.2, we wanted to find H. So for H, we said the change in the potential energy, so in other words, the change in the potential energy is actually a loss. So maybe the best way to present this is to say the magnitude of the change in that is equal to the magnitude of the gain in kinetic energy, or the change in the potential energy is equal but opposite to the change in the kinetic energy, because the potential energy decreases while the kinetic energy increases. So that would be related with a negative sign. So now this change is final potential energy minus initial potential energy equals to final kinetic energy minus initial kinetic energy. Hence, we have the final potential energy is when H is H over 4, and the initial is when H is equal to H. And the change in kinetic energy is final 24.5, which we found in the first part, minus 0. And that gives us H times m, mass of the bob, times G, times 1 minus times 1/4 minus 1, which is minus 3/4, is equal to 24.5. And don't forget, we said the magnitude is what we are dealing with here. So which means the magnitude of h is equal to the magnitude of that. And h will be 0.67 meters. So the height is basically below its initial, measured from below its initial position, as the bulb moves both downwards and to the right. Now the block moves from point B at a velocity of 4.95 meters per second up. So where is let me just show the diagram once more. So after it gets to point B, which is there's no friction, so it continues at constant velocity. Then it gets to this point now. So up a rough inclined plane to point C, the speed of the block at point C is 2 meters per second. Point C is 0.5 meters high above the horizontal, as shown in the diagram. During its motion from B to C, a uniform frictional force acts on the block. State the work-energy theorem in words. The work-energy theorem in words. So that's part 5.2. I think we have stated it earlier, but that was in equation form, work-energy theorem. So how would you state the work-energy theorem in words? How would you state the work-energy theorem in words? What would you say about the work-energy theorem? Yes, you can type something in the comment section or in the chat box. Tell us what you understand by the work-energy theorem. If you are joining us, you can tell us what you think. You can tell us what you think, and let's have fun. If you are having challenges also in with buffering of this stream, just be patient. I'm sure the connectivity challenge has been the order of the day of late. So with the work-energy theorem, the total work done is okay. So you can write it here. The net work or total work, net work done on an object is equal to the change in kinetic energy. Kinetic energy. So we have net work done on an object equal to the change in kinetic energy. So when work is done on an object, that work done will be can be calculated from the change it causes on the kinetic energy of the object. So this is kinetic energy of the object, or the object's kinetic energy. Okay, so